This is Dr. Shankaraiah from Department of Physics. In today's presentation, I am going to discuss a topic in Module 4, which is magnetic and superconducting materials. So, today's topic is hysteresis curve or BH curve in magnetic materials. So, what is hysteresis? And we will discuss what is this BH curve or hysteresis curve in magnetic materials. Okay, if an initially unmagnetized specimen of a ferromagnetic material is subjected to increasing or decreasing magnetic fields, the magnetic field induction varies as a function of H along a closed loop called hysteresis loop. So, hysteresis loop is a BH curve or hysteresis loop is obtained when an initially unmagnetized specimen of a ferromagnetic material is subjected to increasing or decreasing magnetic fields. First, we are going to take a material which is not magnetized. So, the magnetization is 0. Okay. So, this is applied magnetic field H, and this is a magnetic induction B. On y-axis we have magnetic induction, and along x-axis we have applied magnetic field H or magnetic field intensity. So, in the beginning at O, we are taking a material, ferromagnetic material, which is not having any magnetization. So, our magnetic induction is 0. Now, I am taking a ferromagnetic material, for example, iron, which has 0 magnetization or the magnetic induction 0, and now I am subjecting this iron or a ferromagnetic material to increasing or decreasing magnetic fields. I am applying magnetic field. I can increase or decrease it, but I am applying magnetic field to this iron, which is a ferromagnetic material, and then I am looking at the magnetic field induction. How does the magnetic field induction varies as I apply magnetic field along a closed loop? And this observation that how magnetic field induction varies as a function of applied magnetic field is called a hysteresis loop or BH curve. BH curve, where B is applied, B is magnetic field induction and H is applied magnetic field or magnetic field intensity. Okay, so hysteresis loop or BH curve is a closed loop in which we look at the variation of magnetic field induction as a function of applied magnetic field. So, the curve begins at the origin O. So, as you can see here, so at O we have a specimen ferromagnetic material which has 0 magnetic induction, and now as H increased, the field B begins to increase slowly. As we increase the magnetic field in this direction, okay, as I increase the magnetic field in this direction, so I am slowly increasing the magnetic field. As I increase the magnetic field, so this is a variation of magnetic field induction. As I increase the magnetic field induction is also increasing. The dashed line is the first variation of a magnetic field induction as I increase the magnetic field in this direction. Okay. So, as H is increased, the field begins to increase slowly and then more rapidly, and finally attaining a saturation value and becoming independent of H. In the beginning, the magnetic field induction, we have defined what is magnetic field induction. Magnetic field induction B is magnetic flux per unit area. Okay, so the magnetic field induction starting from O, which is 0 at this point O, the magnetic field induction is 0. As I started applying magnetic field in this direction, the magnetic field induction started increasing slowly in the beginning, and as I increased further the magnetic field induction also increased a bit more rapidly now, and it increases to saturate at a field. So around this field, the magnetic field induction became saturated and it becomes independent of magnetic field. That means as you increase the magnetic field further and further, you don't see any change in the magnetic field induction because it reached its saturation value. Okay, so we will discuss what is the meaning of this saturation. Basically, when the magnetic field induction is zero, when you look at the magnetic moments or magnetic spins, all the spins will be oriented randomly, and when you look at the total magnetization, it will be zero. As you increase the applied magnetic field, slowly the spins of these unpaired electrons will slowly get oriented in the direction of magnetic field, and at this point all the spins in the material will be aligned in the direction of magnetic field. Okay, so in the direction of magnetic field, all the spins, unpaired electrons, the spins of all unpaired electrons will orient in a particular direction or in the direction of magnetic field. That is the reason why you are getting a saturation at this point. All the spins of electrons are aligned in the direction of applied field. That is why you find there is a saturation in the magnetization. That is why the magnetic field induction becomes independent above a certain value of applied magnetic field. The maximum value of B is saturation flux density corresponding to magnetization is a saturation magnetization. So yeah, so this is a saturation magnetization that corresponding to saturation flux density Bs, and saturation magnetization is Ms. Okay, so we have defined what is BH curve or hysteresis loop, and then we are now looking at the variation of magnetic field induction, which is defined as magnetic flux per unit area with respect to the applied magnetic field. Okay, thus coercivity is a measure of the magnetic field strength required to destroy. Okay, sorry. Now, so in the first first slide, we have seen that as we increase the applied magnetic field in this direction, the magnetic field induction also increased slowly in the beginning and rapidly as for higher values of applied magnetic field, and it reached saturation above certain applied magnetic field. Now I am reducing the magnetic field, applied magnetic field. Okay, as I decrease, so I have gone up to here. Now I am decreasing the magnetic field. As I decrease the magnetic field in this direction, the magnetic field induction also decreases, but in another path. As I decrease further and further and further, then the magnetic field induction also decreases, but as I decrease the applied magnetic field zero, the magnetic field induction is also decreased, but not to zero, to a finite value. Okay, so it followed, the magnetic field induction followed a path AC as I decrease the magnetic field direction from H to O. Thus B lags behind H. Okay, so B lags behind H. Even though H gone to 0, B has not gone to 0. It reached to a finite value. Okay, so thus B lags behind H. When H becomes 0, B does not become 0 but has a finite value equal to OC. Okay, so this is the value of B. This is the value of B when the applied magnetic field reduced to or decreased to 0. Okay. So this magnetic flux density remaining in the material is called the residual magnetism. Okay, even though we have reduced or decreased the field to 0, the material has not lost its magnetism. It still has some magnetization stored in it. Okay, so this magnetism that is stored even in the absence of magnetic field is called residual magnetism. It indicates that the material remains magnetized even in the absence of an external applied field. Okay, even in the absence of external applied magnetic field, this material has stored some magnetization, and the power of retaining the magnetism is called retentivity or remanence of the material. Okay, so this OC, this is called retentivity. This is the power or ability of a magnetic material, the ability of a magnetic material to store or to retain some magnetization or the magnetism even in the absence of magnetic field is called retentivity or remanence. Okay, retentivity or remanence is nothing but the ability of a material. This is the ability of a material, ability of a magnetic material. The ability of a magnetic material to retain magnetism in the absence of magnetic field. In the absence of magnetic field. The absence of magnetic field. Okay, so retentivity or remanence is the ability of a magnetic material to retain magnetism or magnetization even in the absence of magnetic field. Okay, so here it is OC. So this is the retentivity of this magnetic material. Okay, now what happens if I change the direction of magnetic field to this magnetic material? Okay, let us see what happens to this material if I change the direction of magnetic field. Okay, so if I change the direction of magnetic field, okay, so now what I'm going to do, I'm going to change the direction. So in the beginning I have increased the direction of magnetic field from O to C, O to H, and I've seen that the magnetic field induction increased. As I decrease the field from H to O, I found that the magnetic induction decreases to a finite value, even H reduced to 0. Now, I'm going to reverse the direction. So, in this direction from O, I'm increasing the field in this direction now, and I want to see what happens to this magnetic field induction. As I reverse the direction of applied magnetic field, and I start increasing the applied magnetic field, I find that the magnetic field induction decreases. As I increase further and further, the magnetic field induction decreases to 0 at some point D. As I further increase, the magnetic field induction decreases further and further, and again it reaches a saturation in this direction. So the magnetic field that is required to destroy the residual magnetism is called retentivity, is called coercive force. Okay, so yeah, so we have defined retentivity, which is OC, that is the ability. Here it is given, the retentivity of a material is a measure of the magnetic flux density remaining in the material when the magnetizing field is removed. Okay, now as we reverse the direction of magnetic field, as I increase the field in this direction. Okay, let me erase all this. Now we are in this direction. Okay, so as we reverse the direction of magnetic field and started increasing the magnetic field in this direction, we found that the magnetic field induction decreases to 0 at point D. As I increase further and further the magnetic field, I find this magnetic field induction decreases and reaches saturation even in this direction of applied magnetic field. Okay, so the field that is required, the magnetic field that is required to destroy the residual magnetism, we are destroying the residual magnetism of this material by changing the direction of applied magnetic field and increasing the magnetic field in this reverse direction. We found that the residual magnetism has gone to 0. So the field required to destroy the residual magnetism is called coercive force or coercivity. Okay, so if the magnetic field H is now increased in the reverse direction, the value of B decreases along the path CD. Okay, so yeah, it becomes 0 when H attains a value equal to OD. It means that to reduce magnetic induction within the material to 0, a field of magnitude HC, okay, so this is the field of magnitude HC, must be externally applied in a direction opposite to that of the original magnetizing field. So HC is called coercivity or coercive force. Okay, so we found that we can destroy the residual magnetism by changing the direction of applied magnetic field, and the amount of magnetic field that is required to destroy this residual magnetism is called coercivity or coercive force. Okay, again in this direction also we have found that as we increase further and further, we find that there is a saturation in the magnetic field induction. That means that all the spins of unpaired electrons are again orienting in the direction of magnetic fields. As all the spins of electrons are oriented in the direction of magnetic field, you get a saturation in the direction of applied magnetic field. That is why you find there is a saturation in the magnetic field induction of the material. So thus the coercivity is a measure of the magnetic field strength required to destroy the residual magnetism in the material. Okay. So we are defining coercivity as a measure of the magnetic field strength required to destroy the residual magnetism in the material. As the field, yeah, so we have discussed all this, right? So as the applied field H is increased further in the negative direction, saturation is ultimately reached in the reverse direction, and reversing the variation of applied field, a curve similar to, yeah. So now we have seen up to here. Yeah, so we have discussed. So we have applied the magnetic field in this direction, and then we found there is, as we decrease the applied magnetic field, we find that there is a residual magnetism. Then to destroy the residual magnetism, we have applied the field in this direction, and then we found that the magnetic field induction decreases to 0. But again, as we increase further, the magnetic field induction also increased. It reached a saturation. Now what I am going to do, I am going to again decrease the magnetic field. Whatever I applied increased in this direction, I am going to decrease this magnetic field. As I decrease the magnetic field to 0, again I find that the magnetic field induction reduces to a finite value. Again, the B, magnetic field induction, lags behind H. That means even though I decrease the applied magnetic field to 0, the magnetic field induction has not become 0. It became, or it reached, a finite value, OB. So this is the residual magnetism, and the ability of material that can restore or retain the magnetic field, magnetization even in the absence of magnetic field, is called retentivity. So you have retentivity even in this direction. Now what I am going to do, I want to again destroy this magnetism that is stored in the material. So I am going to change the direction. Again in this direction I am going to apply the magnetic field. As I apply the magnetic field in this direction, I find that the magnetic field induction decreases to 0. As I increase further and further in this direction, I find that the magnetic field induction again increases and the loop closes. Okay. So the closed loop of BH, the closed loop of variation of applied magnetic field induction with applied magnetic field is called BH loop or hysteresis curve. Okay. So at these two points, you can use this material as a permanent magnet. Okay. Yeah, so we find that there is a negative remanence and positive coercivity at points C and F, where the specimen is magnetized in the absence of external magnetic field. It is said to become a permanent magnet at points C and F. So you can use this material at this point C and at this point F as permanent magnet, because there is a magnetism that is stored in the material. The closed curve A, starting from A, C, D, E, F, G, A. Okay, so this closed loop is the BH. The closed loop A, C, D, E, F, G, A represents a cycle of magnetization of the specimen and is known as hysteresis loop of the specimen. Okay, so this is about BH curve or hysteresis loop in magnetic material. So it is basically we are looking at the variation of magnetic field induction or magnetization of a material as we increase the magnetic field and decrease the magnetic field. So we can magnetize a material and we can make the material as a permanent magnet, and we can find out there is some energy loss in a magnetic material as you apply magnetic field. So the area under this curve, the area under this BH curve will give us the energy loss of this ferromagnetic material under magnetic field cycle. So based on the area of hysteresis loop, magnetic materials are broadly categorized into two types, namely soft magnetic material and hard magnetic materials. So based on the area of hysteresis loop, these magnetic materials are classified into two categories: soft magnetic materials and hard magnetic materials. Okay, so the area within a hysteresis loop represents a magnetic energy loss per unit volume of material per magnetization demagnetization cycle. So the area within the hysteresis loop represent magnetic energy loss per unit volume of the material per magnetization demagnetization cycle. So that is what we will discuss. So the energy loss is manifested as heat that is generated within the specimen and raises its temperature. As we apply the field and as we decrease the field, so there is going to be energy loss of this material, and that the energy loss is manifested as heat, and we will find that the material, temperature of the material will be increased because of this energy loss is manifested as heat. And we said that based on this area of the hysteresis loop, magnetic materials are classified into two categories: soft magnetic materials and hard magnetic materials. Magnetic materials which are easily magnetized and demagnetized are known as soft magnetic materials. Easily magnetized and easily demagnetized, these materials are called as soft magnetic materials. They are characterized by thin hysteresis loop. Okay, so if you have this kind of very thin hysteresis loop, these magnetic materials are called as soft magnetic materials because they are going to get magnetized easily and they are also going to get demagnetized easily. Okay, so soft magnetic materials are the materials which can be easily magnetized and easily demagnetized, and they are characterized by this thin hysteresis loop. In applications where the material is subjected to AC fields, materials having narrow and small area hysteresis loop are to be used. Cores of rotating electrical machines are made from this soft magnetic materials. So you can use these soft magnetic materials in cores of rotating electrical machines. Okay, so those are soft magnetic materials which are easily magnetized and easily demagnetized, having thin hysteresis loop. So what are hard magnetic materials? Hard magnetic materials are those which have high resistance to demagnetization and large area of hysteresis loop. Okay, so hard magnetic materials are going to have high resistance to demagnetization, and they are characterized by large area hysteresis loop. A high remanence, high permeability, high coercive field and large hysteresis loop characterize this hard magnetic material. So high remanence, high permeability, high coercive field and large hysteresis loop. So these are the hysteresis loop for hard magnetic materials. So hard magnetic materials are having large area hysteresis loop, whereas soft magnetic materials are having thin area hysteresis loops. So in some applications, the magnetization of the material is to be retained on a permanent basis. Materials with large area hysteresis loop are more suitable for this purpose. Okay, so soft magnetic materials we have used where in rotating electrical machines, whereas hard magnetic materials are used wherever you need a magnetization that to be retained on permanent basis. We can use these hard magnetic materials. So permanent magnets, magnetic tapes and discs are used in entertainment and computer industries are made from hard magnetic materials. So permanent magnets, magnetic tapes and discs, all these materials or devices are made of these hard magnetic materials. Okay, so to summarize in this discussion, in this presentation, I have discussed about hysteresis loop. What is hysteresis loop or BH curve? Okay, and I've also in discussing hysteresis loop, I have also discussed what is retentivity. What is retentivity or remanence of a material, and I've also discussed about coercivity or coercive field. Okay, so finally I have discussed about soft and hard magnetic materials. Soft and hard magnetic materials and applications. Where do we use these materials? Okay, so to revise, hysteresis loop or BH curve is nothing but a closed loop where we look at the variation of magnetic field induction with the applied magnetic field H. Okay, so that is BH curve or hysteresis. Retentivity or remanence is nothing but the ability of a magnetic material to retain some magnetism even in the absence of applied magnetic field. That is retentivity or remanence. Coercivity or coercive field is the amount of field that is required to destroy the residual magnetism. That is called coercivity or coercive field. Based on the area of hysteresis loop, magnetic materials are classified into soft and hard magnetic materials. Soft magnetic materials are the ones which are easily magnetized and demagnetized, whereas hard magnetic materials are the ones which have high resistance to demagnetization. Okay, high resistance to demagnetization. So yeah, so I'm going to close this presentation here, and in the next presentation I will discuss some numerical problems on based on magnetic materials. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.